The last part of this section involves what's called the squeeze theorem. The squeeze theorem is important in a theoretical sense, but you're not going to see much in the way of example problems. Let's look at it though. What the squeeze theorem says is that if we know that there's a function f that's always between these two other functions near the value c, so if f is always in between, and we know that g and h have the same limit there at c, then f being squeezed in between has to have that same limit. And the picture here, I think, does a pretty good job of explaining it. You got one function up here, you got another one down here, and f of x is always in between those, at least when you're close to c. So if these two go together at some point, then this is squeezed in the middle. Let's look at an example. This is an example that's maybe kind of like what you'd see in the homework. The limit, evaluate this limit. Now, technically, I guess we could just plug in 0. The direct substitution rule that we saw before, we didn't say so at the time, but it does apply to trig functions as well. But I want to give an example of how the squeeze theorem works. Notice that sine x is always between -1 and 1. And if you take this and you multiply all three sides of this inequality by x squared, what you get is -x squared sine x times x squared, and then x squared. So what we can do is we can take the limit of these two outer functions. Minus x squared as x goes to 0. That limit's 0. The limit as x goes to 0 of positive x squared, that's also 0. And so since this over here is sandwiched in between, we know that the limit of that function also has to be 0. And if we want to look at this graphically, we can, I've got it shown over here on Desmos. There. So here's the function that we're interested in, x squared sine x. If you look at y equals x squared, it's always above it. Y equals negative x squared is always below it. So when you come in here to 0, x squared sine x has to be in between. All right, that's it.